Okay, so 7.3, we're going to do anti-differentiation by parts. So this is another big rock that you guys are going to take forward to university. Again, don't worry about these ones. There's a different list at the end. So anti-differentiation by parts basically is to undo when the product rule has been used in differentiation. So not all integrals can be used using a simple antiderivative or even by substitution. Okay, so the chain rule as derivatives generally led to substitution as antiderivatives. If the product rule has been used in a derivative, typically our anti-differentiation is going to have to be by parts. So these will be expressed as products where a substitution cannot be found. So how this is going to work is if we have f times g and we take the derivative of it, we get the derivative of the first plus the second, or times the second plus the second times, or the first times the derivative of the second. Then if we integrate both sides, we're doing the antiderivative of the derivative, basically those cancel, and then we're doing the derivative, this whole thing should be in brackets, of f prime g plus f g prime all times dx. So that gives us this, okay? Because these two things, the derivative and then the integral, cancel and give us the original function, and we're integrating both parts here. Now generally what happens and how this gets broken down is that we are given one of these two statements. So we're given fg prime, so we're given something that's easy to do the derivative and something that's easy to do the integral of, and then we have to use this in its rearranged form that's given here to make it into something that is easier to integrate. So this by itself is super hard to integrate, and that's actually given quite commonly. So we have to use what we know about the product rule and differentiation, tie that into integration, rearrange it, and then we're using this formula. So if we're looking for the integral of fg prime dx, that's always going to be equal to f times g minus f prime g dx. Okay, so that comes from this, and then this is like the applicable usage of it. Okay, so it's often simplified to look like this. So these two things are essentially the same thing. I think this is just a little bit easier for us to work with than this. Okay, so we're still looking at, we've got a derivative of 1, that's a derivative of 1, and original. Okay, so same sort of thing, just an easier way to look at it. So this is, I think, what is on your guys' formula sheet. Okay, so this is the one that we're going to use. So the purpose of this and how this is going to work and how it actually makes our lives easier instead of more complicated is we want to identify u and dv in whatever we're being asked to integrate. Okay, now the tricks for this is that if we pick a u, we want it to have an easy derivative. Okay, because if we look at the formula, notice how if we're changing from this into this, we want u to turn into du. So we want to be able to differentiate this and have it be something easier to integrate over here. Okay, and then dv, we want an easy integral. Again, so if we have this, notice how it shows up. We're going to have to do the integral or antiderivative to get this part and this part. So we want those bits to be easy. Okay, so we want this to have a simple derivative, this to have a simple integral. Once we've figured out what needs to be what, then we're actually going to compute. So we're going to take dv and do the integral. We're going to take u and do the derivative. Okay, then we're going to use the simplified definition. We're going to plug it into there to re-express the integral and write it as the antiderivative. Okay, so this seems like a lot, but it does help us. Okay, so some questions may even require you to do it twice or 3 times, but we'll talk about a trick to make that easier later on. So an example, we want the integral of x times e to the 6x dx. Okay, so if we tried to use like parts or anything like that, we could maybe say, okay, well, u is equal to 6x, but then we don't have another x showing up as the du, so like it won't work for that. Okay, so what I see here is this x is a really easy section of this function to integrate. So I'm going to call it u, and then the rest of it is actually a pretty easy function to take the integral of, because we know that the derivative and integrals of e to the x are really, really simple. It's just themselves generally. Okay, so this is going to be our dv. So u is x. So that means du dx, so the derivative of u with respect to x would just equal 1, which means that du by itself is just dx. If we want to integrate 1 dx, that's super easy to integrate. Okay, so that's an aside. So that's good. We've done a good job there. So then dv is going to be e to the 6x dx. Okay, so if we do the integral of both of these sides to get v, then the integral of this, remember that the derivative of e to the 6x would just be e to the 6x times 6, right? Times the derivative of that. So if we're going backwards, we're going to have to put a 1/6 out in front there, and the rest basically stays the same. So if we took the derivative of this to get back to there, we would get there, because that it would multiply by that 6 and get rid of that 1/6. Okay, so pretty easy integral as well. Okay, so now that we've figured out what u, du, dv, and v are, we're going to use our formula up here to replace u dv with this, and it's going to be easier to integrate. So this is u, so u is x times v, so that's 1/6 e to the 6x minus the integral of v, so 1/6 e to the 6x du, so dx. Okay, so see how now this is much easier to integrate than this thing was. We've taken care of the x. So we've already done an antiderivative here and stuck it out here. We've done that. So we've essentially simplified our steps a little bit. Okay, so this thing can just stay as it is, and I'm just going to rearrange it so it's more like what we would see. So 1/6 times x times e to the 6, and then we're doing the integral or antiderivative of this thing. I'm going to pull that 1/6 out, so it's minus 1/6, and then we're doing the antiderivative of just the e to the 6x again, which we've already done, right? So that's 1/6 e to the 6x again. So we can simplify this. We could factor out an e to the 6x if we wanted, but this looks pretty okay. And then anytime we're doing an integral, remember that we have to add that constant on if it's an indefinite integral. There's no boundaries, right? It's not a specific area. We're looking for a family of functions that satisfy this. Our next one we're going to do, so we've got the integral of 3t plus 5 times cos of t over 4 dt. Okay, so again, we need to figure out a u and a dv. So we want u to always be an easy derivative, and then we always want dv to have an easy integral. So out of these two things, if I take the integral of this, it gets more complicated. If I get the derivative of this, it gets easier. So I want to make this one u, because then my derivative is easy. So u is equal to 3t plus 5. So then du dt, it's not a v, is equal to just 3. So that's pretty easy. So then du is equal to 3 dt when we move that dt over. Okay, and then dv is equal to this cos of t over 4, and then that dt is going to come with it because we're doing the integral of both of these sides to give us v. So the integral of cos of something is going to be sine, because we know that the derivative of sine is cos. So sine of t over 4. And then if we did the derivative of this, remember that it would get multiplied by that 1 over 4, the derivative of what's inside. So this must have started as 4 sine of t over 4, because then when we go to this by doing the derivative, the 1, 4, and the 4 would cancel out through multiplication. Okay, so I've got my u, du, dv, and v. Okay, so these integral symbols don't need to be there. So now we're going to break this. This is u, this is all dv, so we're going to replace it according to our formula. So we're taking u, so 3t plus 5, and multiplying it by this v. So 4 sine of t over 4. Then we're subtracting the integral of v, so 4 sine of t over 4, times du, so 3 dt. Okay, so now see how all we've got on this integral that we actually still need to do the integration for is just a sign. The 3 and the 4 is just a constant that can pull out, and this is an easy enough integral as opposed to something like this. Okay, so all of this, I'm going to write it as 4 3t plus 5 times sine of t over 4 minus, I'm going to pull the 12 out, and then we're just doing the integral of sine of t over 4 dt, which is really similar to what we've already done, right? Now we know that the integral of sine is negative cos. And again, if we're thinking about working backwards, so if we wanted to do the derivative of this, we'd get sine of t over 4. Then we'd have to multiply by that 1/4. So there must be a 4 out in front if we're doing the integral. So then simplified, all of this would be 4 3t plus 5 sine t over 4 minus, so negative times negative turns that into a positive actually, so 48 cos t over 4. So there is the integral of that. Okay, because otherwise we don't have any rules for this. We have to split it up. If we do something like this. So remember, we want to pick a u that's going to get more simple with doing the derivative, and we want to pick a v that's not going to get more complicated. So sine and cos are a really good dv, because doing the integral of a sine or cos, generally you're sticking with like one term. It's pretty nice. So we're going to say u is w squared, because then we know du, which would start with that dw under there, is 2w, and then that dw would move up there. Okay, so that's definitely easier. And then the sine 10w, so this was u, this was v. So v is the sine 10w dw. So if we want, or sorry, this is dv. So if we want to figure out what the original of that is, if we want to do the integral of this, then the antiderivative of sine is negative cos. And if I do the derivative of this guy, so the derivative of cos is negative sines, the negatives are going to cancel out, and then I'd have to multiply by a 10. So there had to be a 1/10 in front there, which is why I left so much space. Okay, so now we've got a du that's definitely easier, a v and a or a dv and a v that's not that much more complicated. So we're going to split this. So this is equal to, so according to the formula, we've got the integral of u dv, so that's always going to be equal to u, so w squared, times v, negative 1/10 cos of 10w, minus the integral of v du. So v is negative 1/10 cos 10w times du, so 2w dw. Okay, so we can simplify this a bit. So I'm going to move the negative 1/10 out in front, w squared cos 10w, and then minus, I'm going to pull that 1/10 out in front, so plus 1/10 of the integral of, so this is now cos, I'm going to switch the order of this. So let's go 2w cos of 10w and then dw. Okay, so all the same things. We've got the 2w, we've got the cos of 10w, we've got the dw, and then this is pulled out in front. Okay, so this is easier. We don't have a w squared anymore, but we still, like, if I think about it through substitution and chain rule, like, there wouldn't be a w there. So this is one of those instances where we're going to have to do this again. So we're going to have to use parts twice, because this is now a new u and this is now a new dv. So this is easy to do a derivative of, and it makes it simpler. This is easy to do another integral of. So we've got now u is 2w, so that would make du 2 du dw, so I'm going to just move the dw over there. Then we've got dv is equal to, dv is equal to cos 10w dw. If I do the integral to get v, then the antiderivative of cos is sine, so sine of 10w, and then we must have had that 1/10 out in front, so that if we do the derivative and have to multiply according to the chain rule by 10, that's going to cancel with that guy. Okay, so now we've got, so we're just looking at this. So this is negative 1/10 w squared cos of 10w is all going to stay. Then we've got plus 1/10 of, and I'm going to put a nice big bracket here. Maybe let's even use square ones. So 1/10, and we're just replacing this bit with our new substitution. Oh, you know what we should have done? I made a mistake. Let's pull that 2 out. Let's be smarter humans. This is 2/10. So now we've just got w, which makes this w. That's just a dw. That's even better. So du is equal to dw, and then u is just w. So 2/10 is the same as 1/5. So let's just simplify that. So 2/10 gives us 1/5. And then we've just got w is u, so then du dw is 1. Move the dw over, we got du equals dw. So now we're just using this and using our new rules for replacing. So we've got u, so w times v, so 1/10 sine of 10w, minus the integral of v, so 1/10 sine 10w du, so dw. That's easy to integrate, right? That -1, or that 1/10 is going to pull out in front, and then we can do the integral or the antiderivative of sine of 10w, right? Because now that those other w's are out, we don't have to deal with the w or the w squared that was up there. This is easy. So we've got -1/10 w squared cos of 10w plus 1/5 of, let's write this in a nicer order too. So 1/10 w sine 10w minus the 1/10 is going to pull out in front, and then we're just doing the integral of this. So the integral of sine, or the antiderivative of sine, is a negative cos of that thing. And then remember, if we work backwards, if we do the derivative of this trying to get here, there must have been another 1/10 in front there because of the chain rule. So we could simplify all that. We can distribute that 1/5 in. So let's do that. So we've got negative 1/10 w squared cos of 10w plus 1/5 plus, or times 1/10 is going to be 1/50th w sine 10w. And then plus, oh, this one would be a minus. This time we've got the, oh, no, it would be a plus because we've got another negative here. So you've got a 1/5 times a 1/10 times another 1/10. So this would be 1/500th of cos of 10w. So there is our final integral. And that is a little bit of a pain in the butt. So we're going to get to a point where we can use what we call tabular, it's a table integration, to make that easier on ourselves. We are not going to worry about initial value problems for this, so don't worry about those. We are going to, as I said, use tabular integration to find the antiderivatives. So this one, we've got x to the third, right? We've got x cubed. So that means to get it down to a point where we would have just a number, right? Because ideally, the one where it like worked really nicely, it went away really quickly, du dt or du dx, whatever the variable, is just a number. There's no variable left in it. That would not be the case here for a few rounds. That's why this one took us multiple rounds, because we had to get from a w squared to just a w to just a constant. Okay, so that's why we had to do it twice. This one, we'd have to do it 3 times unless we use what is called tabular integration. So we're going to take the first one, so the one that's going to be easier to do the derivative of, and we'll call that f of x. Okay, and then we're going to take the second one, so in this case that's the one that is easy to do an integral of, and we're going to call that g of x. We're going to split it into a nice little table. Okay, so the part that we have an easy derivative for, so this is an easy deriv, and then this one's a pretty easy integral. Okay, so the side that has the easy derivative, we're just going to take the derivative. Okay, so we're going to start with x cubed, and then we know the derivative of that, is 3x squared. Then the derivative of that is 6x. Then the derivative of that is 6. And then the derivative of that is 0. So basically, we're just going to start with our original, and then in our little table, take the derivative until we get to a 0. Okay, and then we're going to start with the e to the 2x, and we're going to do the integral however many times we need to line up with this 0. Okay, so the integral of this, remember that the integral of e to the something x is always going to be itself, so e to the negative 2x. But if the integral is the opposite of differentiation, anti-differentiation, if we did the derivative of this, we'd have to multiply it by a negative 2. So that would come down and multiply by a negative 1/2 that would have to be there to get back to this. Okay, so then same deal, e to the negative 2x is the easy part, and then we'd have to think about, okay, what would have to be here multiplying with this one to give us this as the derivative? That would be a 1/4, because 1/4 times negative 2 would give us back 1/2. And then e to the negative 2x again. We have to think about what would go here to give us a 1/4, because it's going to be negative 1/8. Then multiply that by 2, or negative 2, we get the negative, or we get the positive 1/4. This time we've got e to the negative 2x, and this one's going to be a 1/16, because that times negative 2 gets us back to negative 1/8. Okay, so we've matched it up. Basically what we do is the top one here doesn't matter and the 0 here doesn't matter. And then we're just going to draw a diagonal line from the first one in the easy derivative category to the second one in the easy integral category. And then a diagonal line, and see how we have an equal number. So they each have a partner, okay? The first one's always going to be a positive, the next one's always going to be negative. Positive, negative, okay? So these are all of our different terms. So our integral of this thing is going to be equal to x cubed times negative 1/2 e to the negative 2x minus this one, 3x squared times 1/4, e to the negative 2x plus 6x times negative 1/8 e to the negative 2x, and then minus 6 times 1/16 e to the negative 2x. Okay, no, you couldn't see any of what I just wrote. There it is. Okay, and then just like on any other antiderivative, we need that plus c to show that this is a family of functions. We could simplify this. I trust that you guys could do that, but just for time's sake, I'm going to skip that part, but that's easy enough to multiply our constants and stuff together. Or sorry, our coefficients. If you want, you can go back and do the last example on the last page again using tabular, and you're going to get the exact same result, but it's going to be way quicker. So you instead of doing by parts multiple times, if it's anything more than like an x squared, even when it is an x squared, I would still do tabular because it's just much easier. So this one's got an x squared, okay, and then a sine of 2x. So this one's easy to do a derivative of. This one's pretty easy to do an integral of. Okay, so this one's going to be, I'm going to use tabular again just to show you that it works on the x squared too. So f of x is x squared, g of x is sine 2x. Okay, so we're going to do the derivatives of this. So x squared is our starting point. Then we get 2x, then we get 2, then we get 0. So we're going to start with sine of 2x. So then the integral of that is going to be cos of the 2x, but that's going to have a 1/2, or sorry, the integral of that's going to be a negative cos, and it's going to have a 1/2, so that when we do the derivative of this, when that 2 multiplies because of the chain rule, it's going to balance back out to a 1. And this one's going to be a negative sine of 2x. There's going to have to be a 1/4 in there to multiply. Then this one's going to be a positive cos of 2x, because the antiderivative of sine is negative cos, and a negative times a negative is going to equal a positive. And then that 1/8 has to be there so that when the 2 gets multiplied, we get back to the negative 1/4. This one doesn't matter, this one doesn't matter. And we draw our diagonal lines. Okay, so our integral of this is going to be x squared times negative 1/2 cos 2x minus, right, because this one's minus, so then 2x times negative 1/4 sine 2x plus 2 times 1/8 cos of 2x. So there's our integral, okay? And we're going to have to evaluate that from 0 to pi over 2. So we'd have to plug pi over 2 in and then subtract into all of this and then subtract what we get when we do 0 in for x's. So I'm going to simplify a little bit first. This is going to be negative 1/2 x squared cos of 2x minus Oh, except for that's going to turn into a plus. So then 2/4 is the same as 1/2 x, and then sine of 2x, and then plus 2 times 1/8 is 1/4 cos of 2x. And that whole thing we're doing from 0 to pi over 2. So, oh my gosh, you couldn't see any of that again. I'm being the worst at this. I will let you catch up. Maybe take a screenshot of this and go back and listen to what I said. Might be helpful. Sorry, guys. Okay, so we're going to have a negative 1/2 pi over 2 squared. And then cos 2 times pi over 2 is just pi. Plus 1/2 pi over 2 sine of pi. Plus 1/4 cos of pi. Minus negative 1/2 0 squared. That whole term is going to be 0, so cos of 0. That's nice. Plus 1/2 times 0, so that whole term is going to be 0, so that's nice. Sine of 0 plus 1/4 cos of 0. So now we have to figure out which ones still are things. So this is all 0, this is all 0. Cos of pi, so here's pi. This is negative 1, 0. So my cos, this is a negative 1. So this is going to be negative 1/2 times pi over 2 squared times negative 1. Sine of pi, this whole thing is 0 because sine of pi is 0. My y-coordinate at that point is 0. And then cos of pi, this is going to be 1/4 times negative 1. And then minus this guy, because that negative is going to distribute, 1/4 cos of 0 is negative 1. Okay, so, hey look, those two cancel. So we just have negative 1 times negative 1 is positive 1. So we have pi squared, 2 squared on the bottom is 4 times another 2 over 8. So we can figure out what that is as a decimal. Okay, to do this, we could also check our answer with the function of integration on our calculator, and whatever decimal we got here, we should also get there. So function integration should match. Okay, so we can still do integrals with boundaries in integration by parts. So this is what I would like you to practice. Those are the types of questions you will see on the take-home test. And then if you have any questions, we can discuss them tomorrow. Okay.